So hello everybody. I'm glad to meet you all this day for our webinar. It's just starting now. So today we will share some information about your possibilities to consolidate mechanical components with metal injection molding and additive manufacturing. So we will talk about how you can improve your cost and your functionality with green part and post-processing. The McKinsey report some days ago had a very interesting conclusion, as I think it's, if you only remember two technologies, they should be additive manufacturing and metal injection molding. And yes, why this? Because I think they are not as wide known, these two manufacturing processes, as conventional, let's say, processes like milling or turning do, and they have a lot of potential for your parts. And what potential and what possibilities to have to use these technologies, that's the point we will discuss now in the following 30 minutes. And I think it's important for you to understand what are these processes, what are the possibilities, what can you do, what will help you, and maybe where are the restrictions, what is the thing you should not do with these processes. One thing at first, it's if you want to be fast, choose the right vehicle. That means for you, if you want to get a part, use the right way to do this, and don't forget it must fit to the road. Means every process must fit to the part or to the design of the part you have. So if you have an existing part, you produce it since a lot of years by milling maybe, and you want to have exactly the same part in MIM or in additive manufacturing, it will be not the best solution for you. It would be better to think of the function of your part, what is necessary to your function, and how should it be designed that the process gives you the right way, and then you get a good solution. And how this works, I will show you in the next slides. But first, some information about both processes that are not as different as you maybe think at the first time. So because we don't talk about every additive manufacturing process, we will focus on additive manufacturing processes which are sinter-based. So sinter-based means we are starting with a metal powder. That's the difference. Normally you start with a hot rolled or cold rolled steel bar. We will start with a metal powder. And this powder is mixed with a binder. We use the binder for making our shape, for getting the powder into a form. At the finished part, we have no binder anymore. We have a complete metal part. And now the difference between AM and MIM is, MIM, you're using a normal injection molding machine. So you have all the possibilities of plastic injection molding process gives to you. And additive manufacturing gives you even more possibilities because you can print it in the 3D shape you want to have. After having the shape of the, call it green part, the mixing of the binder and metal powder, we have some process steps to remove the binder and to get a metal part out of the powder. So first step is debinding, means most of the binder will be removed. And after that, during sintering, the rest of the binder will be removed and the powder sinters together, and by shrinking around 20%, you will reach a nearly closed metal part. So we reach densities around about 96–98% compared to a hot rolled steel. And it's a closed porosity, so the parts are absolutely airtight. Well, MIM or sinter-based AM, which process do you need? Do you want? What are the differences? When do you need AM? When do you need MIM? I'll explain you in the following slides, but whatever you use, the one or the other process, the freedom of design, the possibilities to create complex shapes, the possibilities to mix processes or materials to get clever solutions you won't get in other processes. It's maybe all the same, and all the same is the sinter distortion. You have to consider about it. And to give you a little hint which trick you can use in which process, the following slides. You will get here in the corner left below, you see it, both processes, and you see it can be used or it cannot be used. Well, MIM or sinter-based AM. What's about part size and production volume? So there are different AM processes that are sinter-based. I won't explain that in detail because the webinar number 1 is the better one for you. So if you are interested in the different AM processes and what are they function like and what are their possibilities, so I would think it's better to see the webinar number 1. Just here to see, okay, the size of the part, it's not a thing to decide AM or MIM. Every part size can be used in both processes. But of course, MIM and sinter-based AM, we are limited up to, let's say, around about 150 millimeter. If the parts are bigger than this, it's not cost effective to produce the parts in MIM or sinter-based AM. For smaller parts, down to only a few millimeters, it's no problem with both processes. The bigger difference is the number of parts you need. So MIM is the process for the higher volumes. Why is this so? You need a tool, and the tool is very expensive, so it will cost you maybe 10,000 euros up to 100,000 euros, depending on your shape. And so if you have only a few numbers of parts, it will be too expensive. And AM has the big advantage, you don't need a tool. So one part and the next part, all parts will cost you the same. And what is with part complexity? So if we think about feedstock extrusion, okay, the complexity is more low or medium. But if we don't think about extrusion, if we think of the normally used AM process, so you have perfect complexity. You can go up to the highest complexities of the parts you can ever think. Well, every part you can think, you can design, you can print by AM. That's a fact. And MIM, you can manage a lot of complexities, as you know, from plastic injection molding as well. But some complexities may be too high because you have to demold the parts. You have to deform it, the mold must open and to get the part outside, and that's the limitation of MIM, thinking of part complexity. So if we summarize it in a table, MIM is better for the high volumes, AM is better for the low volumes because you have no tool cost. Surface quality, it depends on the AM process, what's the surface quality like, but the MIM at the moment has the best surface quality of all because of no steps of printing and so on. It's the best quality. So if you need a very, very good quality of the surface, MIM is the better process for you. If you have non-demoldable cavities, so AM is, I think, the only process you can produce such parts. That's how to design a MIM or AM part. I call it Think MIM. And well, what I want to explain is, how do we design machine parts? How do a lot of constructors, engineers think if they design parts? It's like, I think Michelangelo said it very well. He said, I created a vision of my David in my mind and simply carved away everything that was not David. So we construct our parts, we have a steel block, and we remove everything that we do not need. But we remove as less as possible because it's cost time if we remove more than necessary. But the MIM way is very, very different. We come just from the other side. If we design a MIM part, we have nothing. And we think, where do I need some material to get the function I need? So you think from the function side, and you add the material there where you need it from the function side. And so to get very, very different solutions at the end that have the same, same function, but a different shape. Here below, you see on the left side, it's a machine design. You see you have a rectangular block and you remove only these things you need to remove to get your function. On the right side, it's the same function, the same flange, it's a MIM design. So you have only the material there where you need it. And that's the thing, you cannot compare the part price by the design. You must compare it by the function of the part. That's a different way, use a tractor or a car to go to the goal. But if you know this, and if you are ready to change your design of your part and only look on the function, you will get very, very clever solutions. So you can feel free, you can use the design possibilities of the injection process, of the AM process. You're not limited by the milling process and the steel bar you have. And you can save material, you can save resources because you just design the material only there where you need it and not to remove where you need it not. That's it. And so put your parts on a diet, yeah. Try to utilize the design freedom for the MIM process to create lightweight parts. You can save maybe 50% of the weight. Different solutions show this. And okay, it's a green technology, and this will help us. Here, this example is a holder for tape measurement. The original design, the upper one, this was milled. And the MIM solution we developed with our customer got us 50% of weight reduction. Next thing is, if you see on the upper side, it's 3 parts for electronic connector, which goes around the edge. And in the first way, the constructor thought, okay, I have to get very, very easy shaped parts that I can produce by turning maybe. And then you have to assemble these parts, you have the assembling costs, you have the tolerances that they are good to assemble. If you go on this thinking a MIM solution, say, okay, I can do it out of one part because of the freedom of the design. And then you make one part, you have no assembly costs, and to get everything into a mold or print it by 3D printing. And this is, I think, a really new way of thinking if you create some parts. Not only think on your part, think on the surrounding parts. Can I make one part out of 3 or 4 or 2? Will this help me? That's a solution you can only do with MIM or AM. And then, okay, non-demoldable cavities. We discussed this a few slides ago. If you have very, very complex parts, MIM needs demoldable cavities. But if you use AM, sinter-based AM, you can print it. You can print everything you can imagine. You can print these internal structures that are banded. There's no way out if you want to do this in a tool. But by 3D printing, you have the possibilities to create such parts in a very, very easy way. Well, non-demoldable cavities, you have solutions in MIM you can use. If you need a very, very high surface quality and AM is not good for this, or your volumes are very, very high, you have the possibility to use the two-component injection technology that is known from the plastic side. And so you inject one plastic part. So you use only binder in this plastic part and no metal powder. And in the first step, you inject the metal powder, the green part, around this plastic. And after this, you remove the plastic part. And so you have a lost core. And with this lost core, you can handle some non-demoldable cavities. This is maybe sometimes a good solution for you. So if you have the green part and you're sintering, we have a shrinkage around 20%, and we have the gravity, and with a plate where the parts are laid on it, and we have friction. So we have a sinter distortion because during sintering the parts are very weak, and that's something, if you engineer the parts, you have to think of and to handle it. And there are different solutions you can use. One, the easiest is create a flat area that you can position the parts on a flat area, and then they have the stability of the plate they are laying on. That's a best practice, and often it works, but not every time. Here you see a finger follower, and the pedal is not in the middle, as you normally would do, because normally all engineers like to create parts symmetrically. It looks nice and so on. But here it's asymmetrically, it's only on one side. We have a flat surface down below. If this not is possible here, you can give the part a stability so that you have no distortion because the part is stable enough. Here we have a hinge part of a headphone, and with the ribs internally and a very thin wall thickness, so the part is very lightweight, and with the ribs to give the part stability, we have no sinter distortion. So it's possible to do this as well. Or you can add support structures. In other processes, you will do this because it's a lot of effort to get such a support structure. If you want to mill it or so on, it's very, very cost expensive. In MIM or AM, it costs you nothing. Just change your design, add the support structures where you need it, and afterwards you remove them. Most you can break them away, so you have no chips, no lubricant after removing it. It's very cheap to remove the sinter support. That's something you may think of as well. Well then, getting the green part, you have more possibilities to make only one green part in one step. You can combine different materials. We discussed 2K MIM with the lost core to get some forms that you cannot demold. You can use 2 different MIM materials, or maybe 2 different AM materials, and get one metal part out of 2 different metals. Maybe you need a part that combines a magnetic part and not magnetic part. You can combine a 316L and a 174pH. Or you have a part that is in a high temperature, and you need a very, very high temperature resistance. And so you need a nickel-based alloy, an Inconel, and this is very, very expensive, as you know. But maybe not the whole part is in this high temperature. So you can MIM a nickel-based and a steel part just together, sinter it together, and you save money because you have the cheap steel on the side you need, not the high temperature resistant, and you have the nickel-based Inconel on the side you need the high temperature resistance. So There are different possibilities to use this. The only limit is they have to be sintered together. So you need the sintering temperature and sintering atmosphere must be similar. And if you have questions to this, our development team will help us or help you to find the best combination for your demands. But you can not only mix different processes and different materials, you can always mix different processes. You can combine MIM and AM. Maybe you have many parts variants, but a lot of the part or some structures of the part are always the same. So you can MIM this and print on the MIM part. It's possible, and it saves printing time because maybe 90% of the part variance is always the same. You MIM this and then print just the variance on it. Here we have an example of a check valve for a railroad car. Or we can do, we call it co-sintering. Co-sintering means different parts sinter together in the oven. You can use this by use the same process. So MIM two different parts, then assemble them in the green stage, debind and sinter them together, and after that you have one metal part, as it would be one single part. It's another possibility to MIM parts that are not demoldable from their shape. In AM, it's not possible here. You see on the slide, maybe it would be possible, but it makes no sense because assembling green AM parts makes no sense because you can AM them in one time. You can use the co-sintering process not only for non-demoldable geometries, you can use it for very, very fine geometries that are very filigree that you cannot do in the tool otherwise, because the tool would be not stable enough. So you can use this as well. Looking here, you have a nozzle with micro holes, but the micro holes are that micro that you cannot do this in a tool, but you can create two shapes and put them together to create a hole by assemble them. And you can co-sintering by different processes. Make a MIM and a conventional part together. Maybe here in this example, a tube, a very thin wall tube that's too thin to MIM it. It has 0.5 millimeter diameter. And you insert this in a MIM part and sintering together by shrinking the MIM part on the tube. You have one part and they are airtight. Conventional production, you have to mill this cable fiber plug and you have to insert the tubes and then you have to laser weld it, and it's very expensive. And so you save the laser welding if you MIM the part and just assemble it by co-sintering. And of course, you can co-sinter different processes and different materials. So here for injection tool, we had mixed iridium nozzles and an inconel base, because iridium is very, very expensive, but you need it for the function on the nozzle tips. And so on the big volumed center, we can use the much cheaper nickel-based inconel. And so we have conventionally make nozzles on the outer side and a MIMmed inconel base on the inner side and sinter them just together. And of course, think smart. Think about green part processing. Why this? Why this? The green part is a plastic part. If you have a steel that is very, very hard and it's not so easy to machine it, you can machine it in the green part. Because maybe you have a hole only of 0.5 millimeter and you cannot do this in the tool. So you can drill it or laser it in the green part. And you have possibilities to manufacture or to machine your green parts to get some issues on it. and then sinter it. And it's much easier than to make it on the sintered part. And of course, think green, MIM, AM are green technologies. Why are they green? We have no waste. We use 100% of the material we go in that comes out. And it's a lightweight construction, a lightweight process. So you save material by creating your parts. You can recycle parts. And so I think it's just in these days, everything is talking about climate and so on. Just a very, very clever technology.